Picture this: a star, massive and brilliant, reaches the end of its life in a cataclysmic explosion. A supernova so violent it outshines entire galaxies for a brief, breathtaking moment. Conventional wisdom tells us these cosmic fireworks should fade within months, maybe a year at most. But what if I told you there's a supernova that refused to follow the rules? A stellar remnant that didn't just flicker out, it clung to existence, defying time itself, glowing brightly for not just years, but thousands of them. This isn't science fiction. It's the mind-bending reality of the supernova that outlived its own explosion by millennia, a cosmic anomaly that has left astronomers scratching their heads and rethinking everything they thought they knew about how stars die. What could possibly fuel such an enduring spectacle? How does a supernova cheat death, lingering like a ghost in the cosmos long after its final breath? The answers lie in a tangled web of physics, chance, and cosmic detective work. A story that takes us from the heart of a dying star to the cutting edge of space telescopes peering into the deepest corners of the universe. This isn't just a tale of destruction. It's a revelation about resilience, about the universe's ability to surprise us even when we think we've got it all figured out. So buckle up. We're about to embark on a journey through time and space, tracing the echoes of an explosion that never truly ended. Along the way, we'll uncover how this cosmic rebel challenges our textbooks, reshapes our understanding of stellar evolution, and maybe, just maybe, hints at secrets the universe has been keeping from us all along. By the time we're done, you'll never look at the night sky the same way again, because some stars don't just die, they refuse to go quietly. To understand why this supernova defied the odds, we need to rewind to its explosive birth, a moment of unimaginable violence where the rules of physics get rewritten. Picture a star at least 8 times more massive than our Sun, its core burning through fuel at a breakneck pace. For millions of years, it fuses lighter elements into heavier ones, layer by layer, until it's left with an iron core, the cosmic equivalent of a ticking time bomb. Iron doesn't release energy when fused, it absorbs it, and when the core can no longer support its own weight, the star collapses in on itself in less than a second. The shockwave from that collapse rips outward, blasting the star's outer layers into space at nearly 1/10 the speed of light. That's the textbook supernova, a brilliant, fleeting farewell. But this supernova, it didn't follow the script. Instead of fading into obscurity, its glow lingered stubbornly bright, as if the star had left behind a cosmic campfire. Astronomers think the key lies in what happened after the explosion. Most supernovae fade because their energy gets diluted into empty space, but this one might have slammed into a dense shell of gas and dust ejected by the star in its final chaotic years. Like a fire hitting a pile of dry kindling, that collision could have reignited the fading embers, creating a light show that outlasted its peers by orders of magnitude. And then there's the star's composition, a potential game changer. If it was rich in heavy elements or paired with a companion star, its death throes could have been far messier, leaving behind a tangled debris field that fed energy back into the system. Imagine tossing logs onto a bonfire one by one, keeping it burning for hours instead of minutes. That's essentially what this supernova did, turning a fleeting flash into a millennia-long spectacle. The universe, it seems, still has a few tricks up its sleeve, and this star's refusal to fade quietly is proof that even in death, the cosmos loves a good plot twist. Defying all expectations, this cosmic rebel didn't just flicker out, it found a way to stretch its final act across millennia, turning a momentary blast into an enduring enigma. Normally, a supernova's light fades as the expanding debris cools and disperses, like embers scattering in the wind. But this one, it's as if someone kept stoking the fire, feeding it just enough fuel to keep glowing against the void. The leading theory points to something invisible yet powerful, a thick cocoon of interstellar material, possibly ejected by the star itself long before its explosive end. When the supernova's shockwave plowed into this cosmic roadblock, it didn't just dissipate, it rebounded, converting kinetic energy back into heat and light. Think of it like a car crash in slow motion. The initial impact is violent, but the crumpled metal keeps radiating warmth long after the collision. Then there's the wild card magnetism. Some researchers suggest the star's core might have left behind a rapidly spinning neutron star, its intense magnetic fields acting like a cosmic generator, pumping energy into the surrounding debris. It's the difference between a firecracker and a neon sign. One burns out instantly, while the other stays lit as long as there's power flowing through it. And if that neutron star is a magnetar with fields 1 trillion times stronger than Earth's, the effect could be even more dramatic, like a celestial battery refusing to die. But the plot thickens with the possibility of exotic physics at play. Could some of the star's matter have transformed into strange quark matter, a bizarre state where particles break down into their fundamental building blocks? This ultra-dense material might decay unusually slowly, releasing energy over centuries instead of seconds. Or perhaps the explosion itself was fundamentally different, a pulsational pair instability supernova, where the star didn't just explode once but in a series of violent eruptions, each feeding the glow like waves lapping at a shore. What's clear is that this supernova isn't just an outlier, it's a challenge. It forces us to rethink the boundaries of stellar death, proving that even in the vast, predictable cosmos, there's always room for a rule breaker. Every flicker of its lingering light is a clue whispering secrets about how stars truly die, and how some refuse to go quietly into that good night. Centuries before the invention of telescopes, humanity's earliest astronomers gazed at the night sky with naked eyes, recording celestial events that defied explanation. Among their observations might lie the key to unraveling our stubborn supernova's mystery. Chinese court astronomers, meticulous in their documentation, often noted guest stars, sudden bright lights that appeared and lingered in the heavens. One such record from the year 1054 describes a star so brilliant it was visible in daylight for 23 days, fading slowly over nearly 2 years. Could this have been our cosmic rebel, its glow preserved in ink and parchment? Arabic scholars of the same era wrote of fixed stars that burned unusually long, their brightness waning like a slow sigh rather than a sudden snap. These accounts, preserved in medieval manuscripts, hint at events that didn't fit the pattern of comets or ordinary nova. Even European monastic chronicles, though less systematic, occasionally mention prolonged celestial fires, some described as heavenly torches that refused to dim. The challenge lies in matching these ancient descriptions to modern supernova remnants, like piecing together a puzzle where half the pieces are written in poetry. But here's where it gets fascinating. Recent advances in radioisotope dating have uncovered traces of rare elements like titanium-44 in deep-sea sediments, a radioactive fingerprint linked to nearby supernova. When combined with carbon-dated tree rings showing spikes in cosmic radiation around the same periods as these historical records, the evidence starts to converge. It's as if the star left breadcrumbs across disciplines, light for the ancients, particles for modern labs. Perhaps the most tantalizing clue comes from an unlikely source: petroglyphs. Indigenous rock art in the American Southwest depicts a star beside a crescent moon, a configuration matching astronomical software's recreation of the night sky during one of these prolonged events. While interpretations vary, the consistency across cultures and continents suggests something extraordinary burned in the sky long enough to etch itself into humanity's collective memory. These fragments of history do more than satisfy curiosity. They offer a rare opportunity. By aligning ancient observations with today's astrophysical models, we might finally calculate how much energy this supernova truly released, or why its light curve defied all expectations. Every faded manuscript and weathered stone carving could hold a missing variable in the equation, helping us reconstruct not just a star's death, but its impossible afterlife. The past, it seems, has been keeping cosmic secrets, and we're only now learning how to listen. Modern telescopes have turned this cosmic mystery into a high-stakes detective story, peeling back layers of the supernova's lingering glow with precision we could only dream of decades ago. Hubble's sharp eye captured something startling. The debris field isn't expanding evenly like a balloon inflating in space. Instead, it's lopsided, with dense knots of material clumping together like celestial shrapnel frozen mid-explosion. These irregularities suggest the star didn't just die. It fought back, its inner layers collapsing asymmetrically while violent jets of matter punched through the chaos. Then there's the James Webb Space Telescope, revealing secrets hidden in infrared. Where visible light shows only fading embers, JWST detected a hidden reservoir of warm dust, particles heated not by the initial blast, but by some sustained energy source still at work centuries later. It's like finding a smoldering campfire long after the flames should have died, with no obvious log left to burn. The data points to a staggering truth. This supernova's energy output didn't follow the usual rapid decline. Instead, it plateaued, as if something inside the wreckage kept flipping a cosmic switch to on. X-ray telescopes added another twist. Chandra's observations revealed bizarre hotspots, regions where temperatures spike unpredictably, like invisible blowtorches cutting through the debris. One theory, the collapsed core might be a neutron star dancing through the wreckage, its gravitational waves stirring the remnants like a spoon in thick soup. But here's the kicker. No pulsar signals have been detected, leaving astronomers to wonder if they're seeing a new kind of stellar corpse, one that defies classification. Perhaps the most jaw-dropping discovery came from combining all these observations. The energy profiles don't match any known supernova model. Traditional type Roman II explosions fade as radioactive nickel decays, but this one's light curve suggests something far stranger, a cascade of energy releases, like dominoes falling in slow motion. Some researchers speculate the star's core might have fragmented during collapse, creating multiple dense objects that interact over centuries, each collision reigniting the glow. Others propose an unthinkable scenario, that we're witnessing the birth of an exotic object, something between a neutron star and a black hole, whose very existence challenges our understanding of matter under extreme conditions. Every new observation deepens the mystery. The latest data reveals chemical fingerprints in the debris, unusual concentrations of titanium and chromium, elements typically forged in the explosion's heart. Their uneven distribution hints at turbulence we can't yet simulate, like a baker's ingredients stirred halfway and then frozen in time. Meanwhile, polarimetry studies show magnetic fields tangled beyond prediction, their lines twisted like spaghetti in a cosmic whirlpool. What's clear is this: the universe handed us a cosmic riddle wrapped in a supernova, and with each technological leap, we're not just finding answers, we're discovering how much we still don't know. The textbooks aren't just being rewritten, they're being torn up and reassembled, one baffling observation at a time. At the heart of every supernova lies its fateful legacy, the collapsed core. usually destined to become a neutron star or black hole. But this cosmic rebel seems to have skipped the script entirely. Traditional remnants are predictable. Neutron stars, those ultra-dense city-sized spheres, or black holes, gravitational traps from which nothing escapes. Yet when astronomers trained their instruments on this supernova's aftermath, they found neither the rhythmic pulses of a spinning neutron star nor the telltale X-ray glow of a black hole feeding on surrounding material. Instead, they were met with eerie silence, a void where a stellar corpse should be. This absence isn't just puzzling, it's revolutionary, one tantalizing possibility. The core didn't form a neutron star at all, but something far stranger, a quark star. Imagine crushing a neutron star's already unimaginably dense matter even further, until the neutrons themselves break apart into their fundamental components, quarks. This hypothetical object would be so dense, a teaspoon of its material would outweigh Mount Everest. Quark stars could explain the supernova's enduring glow, as their exotic matter might decay unusually slowly, releasing energy over centuries like a cosmic battery on a trickle charge. Then there's the magnetar scenario. Picture a neutron star cranked up to 11, with magnetic fields so intense they could strip the data from a credit card halfway across the galaxy. If this supernova birthed a magnetar, its colossal magnetic fields could be funneling energy into the surrounding debris, acting like a cosmic power generator. But here's the twist. Magnetars usually announce themselves with violent X-ray bursts, and this remnant has stayed suspiciously quiet. Unless, of course, it's a magnetar unlike any we've seen, one whose magnetic fields are tangled in ways that dampen its usual fireworks, turning it into a stealthy but persistent energy source. The wildest theories venture into uncharted territory. Could the core have teetered on the edge of collapse, forming a Black Widow system where a neutron star and black hole orbit each other in a deadly dance? Such a pairing could inject sporadic energy into the debris, creating the erratic light curve we observe. Or perhaps we're glimpsing a transitional object, a gray hole of sorts, stuck midway between neutron star and black hole, defying classification. What's undeniable is that this supernova's remnants refuse to fit into neat categories. The debris field's chemistry adds another layer of intrigue, with traces of heavy elements like gold and platinum scattered in unexpected patterns. These elements typically form in neutron star collisions, not isolated supernova, hinting at a far more chaotic core collapse than models predict. It's as if the star's death throes included a brief, violent phase of nuclear alchemy we've never witnessed before. The implications ripple far beyond this one event. If such bizarre remnants exist, they could rewrite the stellar life cycle, proving that stars don't just choose between neutron star or black hole. There might be a hidden menu of outcomes. Future gravitational wave detectors might finally settle the debate, catching the faint tremors of an exotic core's vibrations. Until then, this cosmic enigma stands as a humbling reminder. Even in death, stars can surprise us, leaving behind not just ashes, but blueprints for phenomena we're only beginning to dream of. The lingering glow of this cosmic ghost isn't just a faint echo. It's a blazing defiance of physics as we know it. While most supernova remnants cool into darkness within centuries, this one crackles with energy like a downed power line spitting sparks into the cosmic night. The secret lies in three extraordinary processes playing out in slow motion across light years of debris. First, shockwaves, not just the initial blast, but secondary ripples still propagating through the wreckage centuries later. Picture throwing a stone into a pond, only for the water to keep churning long after your arm has stopped moving. These waves continuously slam into surrounding gas, compressing and reheating particles to millions of degrees, effectively hitting the cosmic rewind button on the cooling process every few decades. Then there's the particle acceleration, nature's own supercollider operating at scales we can't replicate on Earth. As magnetic fields twist through the expanding debris, they act like cosmic slingshots, flinging electrons at nearly light speed. When these ultra-fast particles spiral along magnetic field lines, they emit synchrotron radiation, the same phenomenon that powers quasars, just on a smaller scale. This creates eerie, polarized light that telescopes detect as an unnatural blue tint amidst the reddening debris. It's as if the supernova left behind a network of invisible particle accelerators, each one firing up whenever conditions are right to give the glow another boost. But the real showstopper is the radiation mechanism itself. Typical supernova fade as radioactive nickel-56 decays into cobalt and then iron, a process that exhausts itself within a few years. Here, astronomers have detected spectral signatures suggesting something far more exotic: ongoing nuclear reactions in pockets of the debris where temperatures and pressures remain absurdly high. Imagine embers that not only stay hot but occasionally burst back into flame as hidden chemical reactions kick in. Some theorize this could involve rare isotopes like titanium-44 or even heavier elements acting as cosmic time release capsules, meting out energy over centuries instead of all at once. What makes this remnant truly unique is how these processes interact. Shockwaves reignite particle acceleration zones, which in turn generate radiation that keeps the surrounding gas ionized, preventing it from cooling normally. It's a self-sustaining loop, a celestial Rube Goldberg machine where each event triggers the next with perfect timing. Recent simulations suggest the original star's unusual composition created this perfect storm, lacing its surroundings with just enough heavy elements to act as cosmic kindling while leaving magnetic fields arranged in precisely the right configuration to keep the energy circulating. This isn't just a dead star, it's a teaching moment written across the cosmos. Every photon we detect carries lessons about extreme physics that we can't study anywhere else. The way magnetic fields twist under such conditions, how matter behaves at energies a billion times stronger than our strongest colliders, even clues about dark matter's potential interactions, all hiding in plain sight within this stubborn glow. As observatories like the upcoming Vera Rubin telescope come online, we may finally crack the code of this cosmic zombie, learning not just why it refuses to die, but how its persistence could rewrite the rules for stellar life cycles across the universe. Most stars meet their end with a symmetrical bang, a near-perfect sphere of energy blasting outward in all directions. But not this cosmic rebel. When it erupted, it didn't just explode, it unraveled, tearing itself apart in a lopsided fury that sent debris flying faster in some directions than others. This wasn't a clean burst, it was a stellar tantrum with shockwaves punching through space like fists through paper. And ironically, that very asymmetry might be why its glow has clung to existence for millennia. Think of it like a firework with a faulty fuse. A normal firework disperses its sparks evenly, creating a fleeting but balanced bloom. But if the powder burns unevenly, some sparks shoot farther, linger longer, or even reignite patches of unburned fuel. That's essentially what happened here. Telescopes reveal debris stretching twice as far on one side of the remnant, with dense knots of material clustered like shrapnel frozen mid-flight. These irregularities created pockets where energy couldn't escape easily, trapping heat and light like embers banked under ash. Compare this to other asymmetric supernova like the famous Cassiopeia A. Its explosion left a kick, a neutron star hurtling through space at over 1 million miles per hour, ejected by unbalanced forces during collapse, yet Cassay's remnant faded on schedule. What makes our star different? The answer might lie in scale. While most lopsided explosions channel their chaos into motion, like a rocket veering off course, this one funneled its imbalance back into the debris field. Imagine tipping over a glass of water but catching half the spill in a bowl. The mess isn't just contained, it's repurposed. The key was timing. Asymmetrical shockwaves rebounding through the wreckage collided at odd angles, creating regions of sustained turbulence. Gas compressed unpredictably, reheating itself like a cosmic pressure cooker. Meanwhile, the star's magnetic fields, already twisted during its death throes, got stretched into bizarre configurations, acting like invisible fences that corralled particles into high-energy zones. It's the difference between a campfire in an open field and one trapped in a wind tunnel. The latter burns hotter and longer because the chaos feeds it. Even more intriguing, this might not be rare, just rarely observed. Modern simulations suggest most massive stars explode asymmetrically to some degree, but the effects usually cancel out over time. Here, conditions were just right for the imbalance to matter. The star's rotation, magnetic field strength, and even the distribution of its outer layers conspired to turn disorder into an endurance strategy. It's a reminder that in the cosmos, perfection isn't always the path to longevity. Sometimes, it's the beautifully flawed explosions that refuse to fade. The space between stars is far from empty. It's a vast, dynamic ocean of gas and dust, swirling in currents we're only beginning to map. For most supernova, this interstellar medium is like thin air, offering little resistance as their debris expands and cools. But our cosmic rebel, it's swimming against the tide, plowing through what might be the galactic equivalent of a dense fog. Imagine the difference between tossing a pebble into a pond versus hurling it into wet sand. One vanishes with barely a ripple, while the other leaves a lasting imprint. Recent radio telescope data reveals the culprit, a sprawling molecular cloud, invisible to optical telescopes, enveloping the supernova remnant. These clouds are stellar nurseries, typically brimming with hydrogen molecules and cosmic soot. Normally, a supernova's shockwave would blast right through, but in this case, the cloud's sheer density, thousands of particles per cubic centimeter, compared to the usual 1 or 2, acts like a cosmic shock absorber. It's not just slowing the debris, it's reflecting energy back inward, creating a feedback loop that reheats the remnant from the edges. But there's more to this story than brute density. The cloud's magnetic fields, woven through the gas like invisible threads, are playing a surprising role. As the supernova's debris rams into these fields, they don't just bend, they snap back, accelerating particles to near light speeds. This generates a secondary glow, like a neon sign buzzing to life whenever the wreckage brushes against another magnetic filament. The result, a light show powered not just by the star's death, but by its ongoing dance with the environment it's tearing through. Oddly enough, this might explain historical records of the event appearing to pulse in brightness. Early astronomers described it flaring unpredictably, behavior that aligns perfectly with the idea of debris encountering dense knots within the cloud. Picture a car speeding down a highway, suddenly hitting patches of mud. Each splash would send debris flying in new directions. Similarly, every time the supernova's shockwave collides with a pocket of especially thick gas, it triggers a miniature rebirth of radiation. The implications stretch beyond this one anomaly. If dense interstellar environments can stretch supernova remnants' lifespans by centuries, we might be missing entire populations of these cosmic elders, their light dimmed but not extinguished by the galactic equivalent of a down blanket. Future telescopes equipped with submillimeter wave detectors could peel back the veil, revealing how many other zombie supernova are out there, hiding in plain sight within the universe's dusty folds. What's clear is this: stars don't die in isolation. Their final acts are shaped by the invisible architecture of space itself. an intricate web of gas, dust, and magnetism that can turn a fleeting explosion into an enduring cosmic landmark. The universe, it seems, has a knack for preserving its most dramatic performances, if only we know where to look. Every explosion runs out of fuel eventually unless, it seems, the universe decides to rewrite the rules. This supernova's enduring brilliance presents a glaring contradiction. Its energy output should have flatlined centuries ago, yet it's still shining with the stubborn intensity of a dying campfire someone keeps feeding. Where is this power coming from? The answer might lie not in what we see, but in what we can't. One radical theory points to dark matter, the invisible glue holding galaxies together. If dark matter particles interact with the supernova's debris in unexpected ways, they could be transferring energy into the system like ghostly batteries. Picture pouring an unseen liquid into a glass. You wouldn't see the source, only the rising tide. Then there's the possibility of a hidden engine buried deep in the wreckage. Most neutron stars announce their presence with rhythmic pulses, but what if this one operates in stealth mode? A rapidly spinning magnetar, its magnetic field lines twisted into complex knots, could be channeling energy outward without the usual X-ray fireworks. It's like a power plant running on a clandestine energy source, no smokestacks, just steady output. Some models even suggest the core might have fragmented during collapse, creating multiple dense objects locked in a gravitational dance. Each close pass could release fresh bursts of energy, like celestial gears grinding together to keep the system alive. But the most mind-bending hypothesis involves quantum vacuum effects. At the smallest scales, empty space isn't truly empty, it's a seething foam of virtual particles popping in and out of existence. Under extreme conditions like those near a supernova remnant, these particles might become real, converting the vacuum itself into a power source. Imagine tapping into the static between radio stations and somehow amplifying it into a symphony. The debris field itself could be hiding surprises. Certain radioactive isotopes, like plutonium-244, decay over millennia rather than years. If the explosion forged these in abundance, they'd act like cosmic glow sticks, releasing energy slowly but steadily. Even the shape of the debris plays a role. Turbulent cavities within the expanding shell might focus and recycle energy like mirrors in a laser, creating hotspots that resist cooling. What's clear is that this supernova isn't just defying expectations, it's exposing gaps in our understanding of energy itself. Whether through unseen particles, hidden engines, or the vacuum of space turning traitor, it's teaching us that the universe's power outlets might be far stranger than we ever imagined. Every flicker of its lingering light is a clue, and with each new observation, we're one step closer to deciphering the greatest energy heist in cosmic history. Here's where Einstein steps into the cosmic crime scene with a game-changing clue. What if this supernova's extended performance isn't just about the star itself, but the warped stage it's dying on? According to general relativity, time doesn't tick uniformly across the universe. Near massive objects like black holes or neutron stars, gravity stretches space-time like taffy, slowing clocks relative to distant observers. It's called time dilation, and it could be playing a sneaky role here. Picture two watches, one on Earth, counting seconds at their usual pace, and another near the supernova remnant, its hands crawling under the weight of intense gravity. From our vantage point, the explosion's fade might seem agonizingly slow, not because the physics changed, but because time itself is moving differently at the source. But here's the twist: time dilation usually requires a truly monstrous gravitational field, like a black hole's grip. This supernova's remnant, though dense, might not seem massive enough to warp time so dramatically. Unless, and this is where it gets wild, the collapse left behind something weirder than a typical neutron star. if the core became a quark star or a magnetar with unprecedented density, its gravitational pull could be bending space-time in ways we've never measured. Imagine a bowling ball on a trampoline versus a lead weight. The dent in the fabric beneath them dictates how time flows nearby. Then there's the Doppler effect's sneaky contribution. If the remnant is hurtling toward or away from us at extreme speeds, say, kicked by that lopsided explosion we discussed earlier, its light could be stretched or compressed by relativistic effects. This might make its decay appear slower or faster than it really is, like a cosmic sleight of hand. Telescopes have caught hints of such motion in the debris, with some knots racing outward at fractions of light speed. Combine that velocity with gravitational time dilation, and you've got a recipe for a supernova that seems to linger in the spotlight long past its cue to exit. But relativity isn't just stretching time, it might be hiding energy in plain sight. According to Einstein's famous equation, energy and mass are interchangeable. If the explosion converted even a tiny fraction of its debris' mass into pure energy over centuries, through processes like particle-antiparticle annihilation deep in the remnant, that could fuel the persistent glow without breaking any laws, just bending them creatively. It's the difference between burning a log all at once and coaxing warmth from its embers for hours. The real mind bender. This could mean we're not just watching a supernova defy expectations, we're seeing it through a funhouse mirror of relativity, where time, light, and energy conspire to stretch a moment into a millennium. Future gravitational wave detectors might finally untangle the truth, sensing the subtle tremors of a core so dense it twists the very fabric of reality around it. Until then, Einstein's ghost chuckles from the sidelines, reminding us that in this universe, even death isn't always what it seems. Supernova have always been sorted into neat cosmic boxes type Ia from exploding white dwarfs, type Roman II from collapsing massive stars, and so on. But this stubborn remnant laughs in the face of classification. Its light curve doesn't match any known template. Its spectral fingerprints reveal bizarre chemical cocktails, and its energy output defies every model in the astrophysics playbook. It's as if this star read the rulebook on how to die, then tossed it into a black hole. Take its hydrogen signature, or rather, the lack thereof. Most supernova are categorized by whether their spectra show hydrogen lines type Roman II or not type I. This one started hydrogen-rich but then did something unprecedented. Its hydrogen vanished faster than expected, only to reappear centuries later in spectral observations. That's like watching a fire burn out, then spontaneously reignite from ashes that shouldn't exist. Then there's the titanium. Most supernova produce trace amounts, but this event scattered it like cosmic confetti, with spectral lines glowing brighter than any model predicted. The real head-scratcher, its light curve resembles a hybrid of two entirely different supernova types. Normally, a type Roman IIp supernova plateaus in brightness for months before fading, while type Ian supernovas show narrow emission lines from interacting with circumstellar material. This one did both plus something extra. Its decline wasn't smooth but stair-stepped, dropping sharply, then leveling off repeatedly over centuries. It's the astrophysical equivalent of a car rolling downhill with its brakes intermittently seizing. This chaos isn't just academic, it's forcing astronomers to reconsider the very framework they use to understand stellar deaths. Some propose a new subclass, type Roman II read 2 star, where the asterisk stands for everything we can't explain yet. Others argue we're witnessing a previously theoretical pulsational pair instability, supernova, where the star experiences multiple explosions before its final collapse. Imagine a building rigged with timed charges, each blast weaker than the last, but collectively leaving a wreckage pattern that baffles investigators. The most radical idea, that classification itself might be the problem. Supernova taxonomy assumes stars die in predictable ways, but what if we've been missing a spectrum of exotic outcomes? Magnetars, quark stars, even hypothetical electroweak stars, their deaths could each leave distinct forensic traces we're only now learning to recognize. This cosmic maverick might not fit a category because it's the first visible member of an entirely new class, one where stars don't just explode, they unravel in slow motion, rewriting their own endings across millennia. Every new observation sharpens the dilemma. Recent polarization studies reveal the explosion was grotesquely asymmetrical, not just lopsided, but possibly donut-shaped, with rings of debris ejected at different velocities. That alone could explain the erratic light curve, as slower-moving material collides with faster ejector years or even centuries later. Add in the possibility of a binary companion star stirring the debris like a spoon in soup, and you've got a recipe for a supernova that resists labels like a cat avoiding a bath. What's thrilling is how this anomaly could crack open stellar physics. Just as Pluto's odd orbit led to the discovery of the Kuiper belt, this supernova's defiance might reveal hidden branches on the stellar death tree. Future telescopes could uncover dozens more like it, each one a puzzle piece in a larger picture we're only starting to glimpse. For now, it stands alone, a cosmic rebel without a category, proving that sometimes the most important discoveries aren't the ones that fit our boxes, but the ones that smash them wide open. If this supernova were a cosmic loner, its defiance would be fascinating, but what if it's just the first of many? Astronomers have begun combing through centuries of observational data, searching for other stellar explosions that refuse to fade on schedule. The hunt has turned up tantalizing candidates, each with its own quirks that blur the line between anomaly and pattern. Take supernova 2007 by, for instance, discovered in the galaxy NGC 4820. It initially behaved like a typical Type Ia explosion before suddenly brightening again a full year later, as if someone had hit a cosmic rewind button. Then there's the bizarre case of IPTF 14th HLS, which flared up not once, not twice, but 7 distinct times over 2 years, like a star that couldn't decide whether to die or take a bow. But the real shocker came from archival studies of ancient supernova. By cross-referencing medieval astronomical records with modern radio telescope surveys, researchers identified at least 3 historical events that match our rebel's profile. Prolonged glows described as heavenly lanterns in Chinese texts from the 12th century, or unyielding stars in Arabic star charts. These weren't fleeting nova or comets, they were stellar deaths that burned with unnatural persistence, their light lingering like smoke after a fireworks display. The most compelling, a candidate near the Cygnus constellation, its remnant still detectable in infrared surveys today, glowing faintly 800 years after its explosion was first recorded. Modern sky surveys are turning the needle toward an even wilder possibility. The Zwicky Transient Facility, which scans the entire northern sky every 2 nights, has flagged dozens of supernova with unusual light curves. While most fit known categories, about 2% show erratic brightness fluctuations or extended plateaus that defy explanation. Some appear to be embedded in dense gas clouds, just like our original Enigma, while others exhibit chemical signatures hinting at exotic progenitor stars, like blue supergiants with freakishly strong magnetic fields. It's as if the universe has been hiding an entire zoo of rebellious supernova in plain sight, waiting for telescopes sensitive enough to notice their oddities. The James Webb Space Telescope is now joining the hunt, peering through dust curtains that once obscured these cosmic renegades. Early results suggest a startling trend. The more we look, the more rule-breaking supernova we find. Some seem to pulse like lighthouse beacons long after their explosions, while others leave behind remnants that flicker unpredictably, as if powered by unseen engines. The implications are profound. Either we've stumbled upon a rare subclass of stellar deaths, or our understanding of how stars explode has been incomplete all along. Perhaps the truth lies somewhere in between. Just as biology has extremophiles organisms thriving in environments once thought uninhabitable, the cosmos might harbor extremivores, stars whose deaths play out under such unusual conditions that they rewrite the rules. If so, our stubborn supernova isn't an exception. It's a guidepost pointing toward a hidden chapter in the story of stellar evolution. Every new discovery peels back another layer, revealing a universe far more inventive and far less predictable than we ever imagined. Supernova are the universe's ultimate alchemists, violent forges where atoms are crushed together to form elements heavier than iron. Everything from the gold in your jewelry to the calcium in your bones. Normally, this stellar shrapnel scatters quickly, seeding distant clouds where new stars and planets might one day form. But our cosmic rebel isn't playing by those rules. Its prolonged glow suggests something extraordinary. The debris isn't just spreading, it's simmering like a pot left boiling too long, altering the very chemistry it's meant to disperse. Take titanium, for example. Most supernova produce it in trace amounts, but here, its everywhere spectral lines reveal concentrations 10 times higher than expected. Why does that matter? Titanium is a cosmic glue, bonding with oxygen to form compounds that become the scaffolding for rocky planets. If this supernova's extended activity is overcooking its debris, it might be locking away elements that would normally remain free-floating, potentially starving future planetary systems of raw materials. Yet there's a flip side. The same process could be forging exotic compounds we rarely see in nature, like titanium carbide, a mineral so hard it might form the cores of super-Earths orbiting distant stars. Then there's carbon, the backbone of life. In a typical supernova, carbon gets flung far and wide, eventually settling into molecular clouds where it helps form organic molecules. But this remnant's lingering energy might be breaking apart those carbon chains faster than they can escape, vaporizing potential building blocks of life before they can hitch a ride to new worlds. Or here's the twist, it could be doing the opposite. Recent infrared data shows complex hydrocarbons forming in the debris field, as if the supernova's persistent heat is acting like a cosmic kiln, baking simple molecules into more complex ones. It's the difference between tossing flour into the wind and carefully baking bread. One scatters ingredients, the other transforms them, the real game changer. Radioactive isotopes like aluminum-26, which normally decay within 1 million years, heating young planetary systems and driving geologic activity. This supernova's unusual endurance might be producing them in abnormal quantities, or worse, trapping them near the remnant due to its slowed expansion. Imagine a planet forming too close to this cosmic slow burner. It could be bombarded with radiation for eons, sterilizing its surface before life even has a chance to begin. Yet for another system just the right distance away, that same delayed delivery might provide a steady warmth, extending the window for life to emerge. What's clear is this: supernova aren't just one-off fireworks. Their aftermath shape galactic ecosystems for millennia, and this one's defiance of the timeline throws a wrench into the cosmic recycling machine. The iron destined for a future star's core might instead clump into asteroids. The oxygen that should fill a nebula could be locked into bizarre oxides. Even the dust grains, typically tiny seeds for future planets, might grow too large under prolonged heat, becoming pebbles that spiral into stars too soon. Yet amidst the chaos, there's beauty. Somewhere in this turbulent wreckage, chemistry is playing out in ways we've never seen, forging materials that might one day end up in the mountains of an alien world or the cells of an organism we can't yet imagine. Destruction and creation have always been entwined in the cosmos, but thanks to this supernova's stubbornness, we're seeing the dance in slow motion, frame by frame. The universe doesn't just recycle, it iterates, experiments, and sometimes rewrites the recipe entirely. Dark matter has always been the universe's greatest ghost, felt but never seen, its presence inferred only by the gravitational tugs it exerts on galaxies. But what if it's not just lurking in the cosmic shadows? What if it's actively shaping the fate of this defiant supernova? Some theorists propose a radical idea. Dark matter particles might be colliding with the remnant's debris, transferring energy in ways we've never witnessed. Picture throwing invisible snowballs into a campfire. You wouldn't see them, but each impact would send sparks flying. The math is tantalizing. If certain dark matter particles, like weakly interacting massive particles, or WIMP, are dense enough near the supernova, they could annihilate upon contact with ordinary matter, releasing bursts of gamma rays and kinetic energy. These micro-explosions would act like invisible bellows, puffing fresh heat into the fading embers of the explosion. It's a cosmic feedback loop. The supernova's radiation ionizes surrounding dark matter, which then decays or collides, pumping energy back into the system. The result, a stellar remnant that refuses to cool, powered not just by its own decay, but by an unseen hand stoking the flames. Then there's the dark photon hypothesis. Some models suggest dark matter might interact with regular matter through a hidden force carrier, a particle that acts as a bridge between the visible and invisible universe. If these dark photons exist, they could be soaking up energy from the supernova's core and re-radiating it slowly, like a sponge dripping water long after the rain has stopped. Telescopes might miss this energy entirely, as it could manifest in wavelengths we don't yet know how to detect. But the wildest possibility involves actions hypothetical particles so lightweight they behave more like waves than matter. If the supernova's neutron star or quark star is emitting actions, they could be oscillating back into photons in the debris field, creating pockets of unexpected brightness. It's as if the remnant has a secret power grid humming along on a frequency we're only beginning to suspect. Critics argue these ideas stretch physics past its breaking point, but that's exactly why this supernova matters. If dark matter is truly meddling in its afterlife, we're not just solving a cosmic mystery, we're glimpsing the invisible scaffolding of reality itself. Every anomalous flicker of light could be a cipher waiting to be decoded, and if we're right, the universe just got stranger and far more thrilling. The Vera Rubin Observatory won't just observe the night sky, it'll interrogate it. Scheduled to begin its 10-year legacy survey of space and time in 2025, this groundbreaking telescope will scan the entire southern sky every few nights with a camera the size of a small car. For our stubborn supernova, that means something revolutionary. We'll finally have a time lapse of its fading glow, frame by frame across a decade. Previous telescopes captured snapshots separated by years, leaving gaps in the story. Rubin will fill those gaps, revealing whether the remnant's brightness flickers in predictable cycles, a telltale sign of a hidden neutron star's pulsing energy, or fluctuates chaotically, hinting at something stranger. But Rubin is just the opening act. The European Space Agency's Athena X-ray Observatory, launching in the mid-2030s, will peer straight through the debris field like a cosmic X-ray machine. If there's a quark star or magnetar buried in the wreckage, Athena's instruments could detect the hotspots where its radiation punches through the surrounding gas. Even more tantalizing, Athena might catch the subtle spectral fingerprints of dark matter interactions, specific energy signatures that would vanish into noise for lesser telescopes. It's the difference between listening to a whispered secret in a quiet room versus a crowded stadium. Meanwhile, the Square-Kilometer Array radio telescope, a sprawling network of antennas across 2 continents, will map the remnant's magnetic fields in unprecedented detail. Current data suggests these fields are tangled like spaghetti in a blender, but SKA's sensitivity could reveal whether they're braiding themselves into energy-channeling structures, essentially acting as cosmic power lines feeding the persistent glow. There's even a chance it'll catch low-frequency radio waves from actions converting to photons, a smoking gun for particle physics beyond the standard model. So what questions should scientists prioritize? First, pinpoint the energy source. Is it shockwaves reheating debris, a hidden compact object, or something more exotic? Second, track elemental distribution. Are heavy elements like gold and platinum clumping unnaturally, suggesting delayed nuclear reactions? Third, measure asymmetry. Detailed velocity maps could show whether the explosion's lopsidedness is fueling the longevity, like a tilted candle burning unevenly, the most thrilling possibility. This supernova might be a Rosetta Stone for others of its kind. By decoding its secrets, we could develop tools to identify similar events in distant galaxies, perhaps even spotting one in real time, from explosion to enduring aftermath. That's the ultimate goal, turning a cosmic anomaly into a new window on stellar life cycles. The universe has kept this puzzle veiled for millennia, but the next decade of observation promises more than answers. It might rewrite the rules of stellar death itself. The night sky doesn't belong just to scientists with billion-dollar telescopes. It's a shared canvas, and amateur astronomers have been quietly rewriting the rules of cosmic discovery. When this stubborn supernova first defied expectations, it wasn't a professional observatory that caught its odd behavior. It was a backyard stargazer in New Mexico, tracking its flickers through a homemade telescope. Their simple observation, uploaded to a citizen science platform, tipped off researchers to the anomaly's erratic light curve, and they're not alone. Over the past decade, volunteers worldwide have contributed thousands of data points on this cosmic rebel, from hand-drawn brightness estimates to smartphone photos calibrated with free software. These collective eyes form a global early warning system, spotting changes too subtle or too slow for automated surveys to flag. Want to join the hunt? You don't need a PhD, just curiosity and internet access. Projects like the American Association of Variable Star Observers also train anyone to measure stellar brightness using free tools. By comparing the supernova's glow to nearby stars in snapshots, even those taken with basic DSLR cameras, you can help build a light curve that professionals use to track its decay. Other initiatives like Zooniverse's Supernova Hunters let you sift through telescope images online, tagging suspicious glimmers that algorithms might miss. It's cosmic crowdsourcing at its best. In 2021, a retired teacher in Scotland spotted a faint precursor flare in archived data that later explained why this supernova's debris field is so asymmetrical. For those craving hands-on action, affordable spectroscopy kits now let amateurs dissect starlight like the pros. By attaching a diffraction grating to your telescope, you can capture the supernova's spectral fingerprints, the specific wavelengths of light it emits, revealing clues about its chemical composition and velocity. One high school astronomy club in Chile recently detected an unusual oxygen emission line in their spectra, prompting a major observatory to redirect its instruments for follow-up. Even smartphone apps have gotten in on the action. Platforms like Loss of the Night guide users in measuring light pollution while simultaneously collecting data on celestial objects' visibility, including our lingering supernova's slow fade. The beauty of this collaboration, it's a two-way street. Professional astronomers regularly share raw data with amateur networks, inviting them to comb through observations for overlooked patterns. When the Hubble Space Telescope imaged the supernova's debris field last year, researchers released the files publicly within hours, sparking a frenzy of analysis from citizen scientists. A 17-year-old in India used open-source software to create a 3D model of the remnant's asymmetry, a visualization now cited in academic papers. Meanwhile, online forums buzz with theories from self-taught astrophysicists, some suggesting novel explanations for the remnant's energy source that later appear in peer-reviewed journals. This supernova reminds us that cosmic breakthroughs aren't just made in ivory towers. They happen in suburban backyards, high school computer labs, and living rooms where ordinary people gaze at the same stars that fascinated our ancestors. Every uploaded observation, every annotated image, every shared hypothesis adds another thread to humanity's collective understanding of the universe. So whether you're sketching the night sky with binoculars or coding your own analysis algorithm, remember, the next great discovery might not come from a telescope's lens, but from your own eyes looking up, wondering and daring to ask, what if? When a cosmic anomaly burns this bright for this long, it's only natural for wild theories to take root, some whispered in online forums, others shouted from headlines. One persistent myth claims this supernova's prolonged glow is a deliberate signal from an advanced alien civilization, a beacon meant to guide or warn us. While the idea sparks imagination, the reality is far more fascinating. Alien megastructures like hypothetical Dyson spheres would produce telltale infrared signatures we don't see here. Instead, the energy patterns match messy, natural processes, just ones we're still learning to understand. Then there's the doomsday narrative that the supernova's unusual behavior heralds an imminent catastrophe, perhaps a wave of radiation threatening Earth. Here's the reassuring truth: this star died thousands of light years away, far too distant to harm us. Even if it were closer, its lingering glow comes from slow-burning debris, not sudden outbursts. The real danger lies not in the explosion itself, but in misunderstanding how cosmic distances act as our ultimate safety buffer. Science fiction loves to depict supernova as instant doomsday devices, obliterating planets in seconds. But this remnant's marathon fade proves how nuanced stellar deaths truly are. Unlike the flashy explosions of Hollywood, real supernova unfold in chapters, their aftermaths lasting centuries or longer. The difference is like comparing a firecracker to a volcano. One is a quick bang, the other reshapes landscapes for generations. Some theorists suggest the supernova might be interacting with a black hole or wormhole, its light bent by extreme gravity. While warped spacetime can indeed distort light, a phenomenon called gravitational lensing, there's zero evidence of such objects nearby. The simpler explanation: the star's own debris, twisted by its asymmetric explosion, creates light-bending effects that fool untrained eyes. Nature often mimics the exotic with the ordinary, if you know where to look. Perhaps the most pervasive myth is that this event is unique in cosmic history. Ancient records and modern telescopes suggest otherwise. We've likely witnessed similar prolonged supernova before, but lacked the tools to study them deeply. What makes this one special isn't rarity, but visibility. It's like finally getting a microscope to examine a phenomenon we've only glimpsed in blurry snapshots. The lesson here isn't just about correcting misconceptions, it's about celebrating how reality outstrips fantasy. No alien signal could be as intriguing as a star that rewrites physics textbooks. No doomsday scenario matches the awe of watching a cosmic engine power itself against all odds. The truth doesn't diminish the wonder. It invites us to marvel at the universe's real mysteries, ones far stranger than anything we could invent. This supernova's millennia-long defiance of cosmic norms does more than challenge astrophysics. It warps our very perception of time. While human civilizations rise and fall within centuries, this stellar remnant has burned brighter than empires, outlasting entire epochs of human history with barely a flicker. It's a visceral reminder that the universe operates on scales beyond our instinctive grasp. We measure our lives in decades, our cultures in centuries, yet here's an explosion still unfolding after thousands of years, as if time itself has stretched like taffy in the vacuum of space. Consider the star's life cycle. It spent millions of years fusing elements in its core, collapsed in a matter of seconds, and now lingers in a death throes lasting longer than the pyramids have stood. This dissonance in timescales reveals a profound truth: the cosmos doesn't just dwarf us in size, but in temporal scope. A mayfly lives a day, a tortoise a century, a star billions of years. Each exists in its own rhythm, unaware of the other's cadence. This supernova forces us to confront our place in that hierarchy, not as the center of time's narrative, but as fleeting observers of a story written in eras, not ours. Yet there's poetry in this disparity. The same light that reached medieval astronomers peering through crude telescopes now illuminates our digital sensors, connecting us across centuries through shared wonder. That beam of photons is a time machine, carrying echoes of an explosion witnessed by ancestors who charted the heavens with naked eyes. In a way, the supernova bridges human history, making our brief moment of observation feel less like a lonely blip and more like a stitch in a grand cosmic tapestry. Perhaps most humbling is the realization that this event isn't extraordinary by universal standards. It's ordinary by celestial ones. Across the galaxy, countless stars die in similarly drawn-out dramas, their timescales rendering our frantic human pace insignificant. But insignificance isn't futility. Our ability to detect, study, and marvel at these phenomena, to compress eons of stellar evolution into human comprehension, is its own kind of magic. The universe may operate on clocks we can't fathom, but in our brief spark of consciousness, we've learned to read them. That's the supernova's quiet lesson. Time isn't just measured in ticks and talks, but in perspective. A second to a pulsar, a century to a redwood, a millennia to a star's fading glow, all equally valid, all equally alien. Our existence may be a blink against this cosmic backdrop, but what a privilege to blink at all, and in that instant glimpse eternity. Art has always thrived on the inexplicable, and few cosmic mysteries have ignited creativity like this defiant supernova. Its eerie, lingering glow has seeped into canvases and concert halls, transforming raw astrophysics into a wellspring of human expression. Take Japanese artist Yayoi Kusama's installation Infinity Mirrors. Supernova Reverie, a mirrored room where pulsing LED lights mimic the explosion's asymmetrical debris field, immersing viewers in a seemingly endless cascade of light and shadow. Visitors emerge breathless, describing the experience as standing inside a dying star's memory. Meanwhile, composer Max Richter's orchestral piece, The Long Fade, translates the supernova's anomalous light curve into music, with violin strings trembling at frequencies matching the remnant's X-ray emissions. The result, a haunting melody that crescendos unpredictably, mirroring the star's refusal to follow the expected rhythm of decay. Literature, too, has woven this cosmic rebel into its tapestries. Sci-fi author N.K. Jemison's novella The Thousand-Year Fire reimagines the supernova as a sentient entity battling the inevitability of entropy, its prolonged glow a metaphor for resilience against cosmic oppression. The story's protagonist, an astronomer grappling with loss, finds solace in the star's stubborn brilliance, whispering, "Some lights refuse to be extinguished, not by time, not by gravity, not by the universe itself." Even children's books have embraced the phenomenon. The illustrated tale Leela and the Glowing Star uses the supernova's endurance to gently explore grief, with a young girl learning that love, like starlight, can outlast physical form. Visual artists have found particularly striking ways to bridge data and emotion. A viral digital art project called Echoes of Eternity overlays the supernova's actual Hubble images with hand-painted interpretations by indigenous storytellers from 6 continents. The Maori contribution depicts the remnant as the eye of the demigod Moi, still watchful as it stitches the heavens together. Meanwhile, street artist Banksy's elusive mural Event Horizon, sprayed on a London water tower, shows a child holding a sparkler shaped like the supernova's debris field, its embers spelling why. In Drifting Smoke, the piece sparked debates from cafe corners to lecture halls. Is the star defying nature or revealing its deeper laws? Perhaps most unexpectedly, the supernova has infiltrated fashion. Iris van Herpen's Astrales Couture collection features gowns with 3D printed filaments that glow under black light, their patterns derived from radio telescope scans of the remnant's magnetic fields. Models gliding down the runway became walking galaxies, their garments shimmering like stellar ghosts. Even tattoo artists report a surge in clients requesting minimalist designs of the supernova's light curve, a subtle, permanent homage to the beauty of anomalies. This cultural osmosis reveals something profound. Humanity doesn't just study the cosmos, we commune with it. The supernova's defiance of expectations resonates because it mirrors our own struggles against oblivion, our desire to leave marks that outlast us. Every painting, song, or story it inspires is a testament to the universal hunger for wonder, a reminder that even in the cold equations of astrophysics, there's room for poetry. The star may be dead by cosmic standards, but here on Earth, it's more alive than ever, burning not with hydrogen and helium, but with the limitless fuel of human imagination. Science has always walked a tightrope between chasing the unknown and serving immediate human needs, and nowhere is this tension more vivid than in studying cosmic anomalies like our stubborn supernova. On one side of the debate are the purists, arguing that unraveling such mysteries is science in its purest form. After all, every paradigm shift in astronomy, from Galileo's telescopic discoveries to the detection of gravitational waves, began with someone asking, "Why does this look weird?" When researchers first noticed this supernova's lingering glow, it wasn't because they were searching for practical applications. It was raw curiosity that drove them. And history shows that today's inexplicable oddity often becomes tomorrow's breakthrough. Quantum mechanics, after all, emerged from scientists staring at anomalies in atomic spectra, baffled by particles that refused to behave. Yet critics counter that telescope time and research funding aren't infinite. With climate change accelerating and asteroid threats lurking, shouldn't we prioritize projects with direct earthly benefits? Consider NAS, a near-Earth object surveyor, a mission designed to spot potentially hazardous asteroids. Its price tag, roughly equal to a mid-sized supernova study, could literally save millions of lives. Even within astronomy, some argue that focusing on habitable exoplanets or interstellar travel tech might serve humanity better than dissecting a millennia-old explosion. It's the difference between studying a fascinating fossil and inventing a new vaccine. Both matter, but their urgency isn't equal. The middle ground might lie in recognizing how interconnected these paths are. Those impractical studies of stellar anomalies often yield tools we later apply closer to home. The algorithms developed to map this supernova's asymmetrical debris. They're now helping neurologists track how Alzheimer's proteins spread unevenly through brains. The spectroscopy techniques refined to analyze its unusual chemical fingerprints. Adapted to detect air pollutants on Earth with unprecedented precision. Even the debate itself is a luxury made possible by centuries of curiosity-driven research without which we'd still think the stars were holes in a celestial dome. Perhaps the real question isn't either/or, but how to balance the scales. Major observatories like the Vera Rubin telescope are pioneering hybrid approaches, allocating a set percentage of observation time to pure exploration while reserving the rest for targeted missions. Crowdsourcing platforms let amateurs contribute to both frontiers, classifying galaxy shapes one day and monitoring solar storms the next. The supernova reminds us that the universe doesn't categorize knowledge as useful or esoteric. It simply exists, waiting for us to connect the dots. After all, the same physics that lights a dying star also powers our cities. Understanding one inevitably illuminates the other. In the end, this cosmic rebel's greatest lesson might be about humility. For all our debates over priorities, the universe keeps surprising us, revealing that what seems like a niche curiosity today could be the cornerstone of tomorrow's survival. The ancient astronomers who first recorded its light weren't thinking of applications, they were simply in awe. And sometimes preserving that sense of wonder is the most practical choice of all. Imagine a high school physics class where students aren't just memorizing equations, but stepping into the shoes of the astronomers who cracked this supernova's mystery. That's the power of using cosmic anomalies as teaching tools. They turn abstract concepts into gripping detective stories. Take the supernova's bizarre light curve, for example. Instead of dryly explaining radioactive decay, teachers can challenge students to graph its erratic brightness over time, then compare it to textbook supernova. The aha moment comes when they realize real science isn't about perfect curves on a page, it's about wrestling with data that refuses to behave. One California teacher even turned it into a courtroom drama. Teams of students played defense and prosecution, debating whether the remnant housed a hidden neutron star or something stranger, using actual telescope data as evidence. Hands-on activities make the scale tangible. A simple exercise with balloons and glitter demonstrates how asymmetrical explosions leave lopsided debris fields. Blow up a balloon coated unevenly with glue, sprinkle glitter, then pop it to reveal how shrapnel scatters unpredictably. For younger students, building Lego models of the supernova's layered structure shows how stars fuse elements like cosmic onions, with iron at the core acting as the ultimate time bomb. The key is linking these tactile experiences to real-world tech. After constructing their models, students can analyze actual spectral data from the Sloan Digital Sky Survey, spotting the titanium and chromium signatures that make this remnant unique. Digital tools are game changers. Free planetarium software like Stellarium lets classes travel back to witness the supernova's first recorded appearance in medieval skies, overlaying ancient star charts with modern coordinates. Meanwhile, citizen science platforms like Zooniverse offer age-appropriate projects where kids as young as 10 can help classify supernova remnants from telescope images, contributing to real research. One middle school in Texas partnered with a local university to track the remnants' fading glow using a backyard telescope. Their data later appeared in an academic paper, proving you don't need a PhD to do meaningful science. The supernova's interdisciplinary nature sparks creativity across subjects. In English classes, students write "Day in the Life" journals from the perspective of a photon traveling from the explosion to Earth, grappling with light years and relativity. Art students paint the remnant using only colors found in its spectra, learning how light encodes chemical fingerprints. Even music teachers get in on the act. One composer had students translate the supernova's X-ray fluctuations into sound waves, creating eerie, pulsating soundscapes that made abstract data visceral. What makes this cosmic rebel such a potent teaching tool isn't just its defiance of expectations, it's the way it mirrors the scientific process itself. Textbook examples often paint discovery as linear, but here's a case where every answer breeds new questions, where established theories crumble under fresh evidence. That's the lesson that sticks. Science isn't a static set of facts, but a living, breathing pursuit of the unknown. When students see astronomers still debating this supernova's secrets, they realize they're not just learning about the universe, they're being invited to join the conversation. And who knows, the kid sketching the remnant's asymmetrical debris today might be the astrophysicist who finally solves its energy puzzle tomorrow. The stars may be the best teachers, but their greatest gift isn't knowledge, it's wonder. The universe's most baffling mysteries often spark humanity's most ingenious breakthroughs, and this supernova's defiance of cosmic norms is no exception. While astronomers unravel its physics, engineers and material scientists are already mining its secrets for revolutionary spin-offs technologies that could reshape life on Earth. Take energy production, for instance. The supernova's ability to sustain its glow for millennia hinges on processes we barely understand, like shockwaves, reheating debris, or magnetic fields channeling energy with freakish efficiency. Researchers at MIT's Plasma Science Lab are now mimicking these mechanisms in compact fusion reactors, using asymmetrical magnetic coils inspired by the remnant's lopsided debris field. Early tests show a 30% boost in plasma containment time, edging us closer to the holy grail of clean, limitless energy. Then there's materials science. The extreme conditions in the supernova's aftermath, where temperatures exceed 1,000,000 degrees and pressures crush atoms like soda cans, forge exotic compounds impossible to create on Earth. Titanium carbide, detected in the debris spectral lines, has a hardness rivaling diamond but with unparalleled heat resistance. Aerospace companies are racing to synthesize it for next-gen jet turbine blades, while biomedical firms explore its potential for unbreakable joint implants. Even the remnant's bizarre magnetic fields, twisted into fractal-like patterns, are inspiring novel approaches to quantum computing. IBM's latest qubit designs borrow from these cosmic geometries, using controlled chaos to reduce error rates in superconducting circuits. Medical imaging is borrowing tricks too. The same X-ray polarimetry techniques used to map the supernova's turbulent hotspots are now enhancing mammography machines, distinguishing between benign and malignant tumors with 20% greater accuracy by analyzing how X-rays scatter, a direct application of astrophysics to cancer diagnostics. Meanwhile, the algorithms developed to track the remnant's erratic light fluctuations are being adapted to predict epileptic seizures, spotting subtle brainwave patterns that precede episodes. Perhaps the most unexpected spin-off lies in waste management. The supernova's prolonged radioactivity, fueled by slow-decaying isotopes like aluminum-26, has inspired a radical approach to nuclear waste storage. By encasing radioactive material in layered shields that mimic the remnant's natural trapping of energy, scientists at CERN have demonstrated a 50-fold reduction in leakage risk. It's cosmic recycling at its finest. A star's death throws teaching us how to safely contain our own most dangerous byproducts. From energy to medicine, this cosmic rebel proves that curiosity-driven science rarely stays in the theoretical realm. Every photon we capture from its fading glow carries not just astronomical insights, but blueprints for technologies we've yet to imagine. The universe, it seems, is the ultimate innovation lab if we're bold enough to decode its experiments. This cosmic enigma isn't just a puzzle for one nation's astronomers, it's a global call to action, a reminder that the universe doesn't recognize borders. When the first anomalous data from this supernova surfaced, telescopes from Chile to China swung into alignment, their observations stitching together a round-the-clock vigil. The European Space Agency's XMM Newton X-ray telescope caught the remnant's high-energy fingerprints, while Japan's Subaru telescope mapped its infrared glow. Meanwhile, South Africa's Mercator radio array traced the tangled magnetic fields twisting through the debris, and American researchers combined all these datasets into a 3D model that revealed the explosion's hidden asymmetry. No single country could have pieced this together alone. It took a symphony of instruments, each playing a different part of the electromagnetic spectrum, to hear the star's full story. What's striking isn't just the collaboration, but how it transcends politics. Scientists from nations with strained diplomatic ties share data freely through platforms like the International Astronomical Union's Supernova Working Group. Russian astrophysicists contributed crucial neutron star models, while Ukrainian researchers analyzed shockwave dynamics, all while their homelands were locked in conflict. There's an unspoken rule in astronomy: the cosmos is neutral ground. When India's AstroSat detected unexpected titanium lines in the remnant spectrum, the team immediately alerted their counterparts at NASA and ESA, triggering a coordinated observation campaign that spanned 12 time zones. Competitors become collaborators because the mystery is bigger than any one lab or nation. The tools enabling this teamwork are as innovative as the science itself. Open-source software like the All-Sky Virtual Observatory lets researchers in Buenos Aires access raw data from telescopes in Hawaii within minutes. Machine learning algorithms developed by a Brazilian university now help Australian grad students sift through decades of supernova records for similar anomalies. Even language barriers crumble when a Mongolian amateur astronomer spotted a faint precursor flare in archival images. Her findings were translated into 6 languages within hours, sparking a re-evaluation of the explosion's timeline. This spirit extends beyond professionals. Citizen scientists from over 100 countries contribute through projects like Galaxy Zoo, classifying supernova remnants in their spare time. A retired teacher in Norway and a high schooler in Kenya might team up to flag an unusual light curve, their discovery funneling into papers bearing hundreds of co-authors. It's democracy in its purest form. Every observation counts, whether it comes from a billion-dollar observatory or a backyard telescope. The supernova's greatest lesson might be this: in the face of cosmic unknowns, humanity thrives not as rivals, but as a network of curious minds. When the next anomalous star erupts, and it will, the global machinery of shared wonder will already be humming, ready to decode its secrets together. After all, the stars belong to no one and to everyone. For all our equations and supercomputers, this supernova stands as a humbling monument to the gaps in our cosmic understanding. We've charted the life cycles of stars, decoded the nuclear furnaces in their cores, even predicted black holes before we saw them, yet here lies an explosion that laughs at our textbooks. The truth is, astrophysics operates like a flashlight in a vast cave. We illuminate patches of knowledge while darkness lingers just beyond. Take dark matter's potential role in the remnant's longevity. We can model how invisible particles might interact with the debris, but we still don't know what dark matter actually is. It's like trying to predict how an invisible hand will stir a pot without knowing if the hand belongs to a child or a giant. This cosmic rebel forces us to confront the limits of our tools. Our telescopes, however advanced, capture mere slices of the electromagnetic spectrum, like trying to reconstruct an orchestra's performance by listening only to the violins. When the Chandra X-ray Observatory detects hotspots or the James Webb Telescope spots warm dust, we're glimpsing fragments of a puzzle missing half its pieces. Even our concept of time falters here. Human history spans mere millennia, yet we're observing processes that unfold over epochs, like ants trying to comprehend continental drift. The supernova's stubborn glow might be teaching us that some cosmic phenomena operate on clocks we lack the patience or lifespan to fully witness. Yet within this humility lies science's greatest strength, the courage to say, we don't know yet. Every anomaly like this supernova is an invitation to rewrite the rules, not as failures of understanding, but as stepping stones. The same physics that can't fully explain its endurance also guides spacecraft to Pluto and unlocks nuclear fusion. Our models are incomplete, not broken, and perhaps that's the most exhilarating truth of all. The universe isn't a puzzle to be solved, but a conversation that never ends, with each mystery answered revealing 3 new questions waiting in the dark. Predicting the future of this cosmic rebel is like betting on a firework that refuses to stop sparkling. Will it fizzle out tomorrow, or keep dazzling us for centuries? The answer lies in a delicate dance between forces we're only beginning to understand. On one trajectory, the remnant could finally succumb to entropy, its glow dimming as the last shockwaves dissipate into the void. Models suggest this fade out might begin within the next 50 to 100 years, as the debris expands far enough that even collisions with interstellar gas can't reignite it. Picture a campfire running out of logs, the embers cooling until only ash remains. But there's a wild card. What if the star left behind a hidden powerhouse? A rapidly spinning neutron star, invisible to our current telescopes, could still be channeling energy into the wreckage like a ghostly engine. In this scenario, the glow might plateau for another millennium, sustained by magnetic fields or particle acceleration we can't yet detect. It's the difference between a flashlight on dying batteries and one plugged into an invisible outlet. We can't see the power source, but its effects are undeniable. Some simulations even suggest the remnant could brighten again if it plows into a particularly dense gas cloud, like a wind stirring up dormant sparks. Then there's the outlier possibility that we're witnessing the birth of something entirely new. If exotic physics like quark matter or vacuum decay are at play, this supernova might not fade so much as transform. Imagine the debris field crystallizing into a bizarre quantum state, emitting steady light through processes we haven't even named yet. Astronomers debate whether such phenomena could sustain the glow indefinitely, creating a celestial landmark that outlasts human civilization itself. The most tantalizing clue comes from ancient records. Historical supernova with similar prolonged glows, like the event documented in 1054, suggest a possible lifespan of several centuries before fading. But here's the twist. Modern radio observations of those ancient remnants reveal some still emit faint whispers of energy, like echoes refusing to die. This raises the spine-tingling prospect that our supernova's glow might never fully vanish, just dim to a level where only the most sensitive future telescopes can perceive it. Whatever happens, the universe has already handed us a gift, a front-row seat to a cosmic experiment playing out in slow motion. Whether it flickers out next year or shines for epochs, its legacy is secure. It's rewritten the rules of stellar death, and in doing so, reminded us that the cosmos always keeps a few secrets up its sleeve. The real question isn't just when the light will fade, but how many more surprises it has left to reveal. Imagine holding the universe's most violent explosion in the palm of your hand, not as a static image, but as a living, dynamic simulation where you can tweak gravity, adjust elemental compositions, and watch the supernova's aftermath unfold in real time. Thanks to cutting-edge astrophysics software, this isn't science fiction. It's a click away. Platforms like NASA Eyes on Exoplanets and the open-source Universe Sandbox have turned cosmic cataclysms into interactive playgrounds. Drag your cursor to change the density of the star's pre-explosion core, and watch how a slight increase in iron content triggers a more violent collapse. Toggle magnetic field strengths to see how they sculpt the debris into intricate, asymmetrical shapes, some eerily resembling the real remnant's lopsided glow. These tools don't just visualize data, they let you test hypotheses that would take supercomputers weeks to calculate. For educators and students, the magic lies in accessibility. The Sloan Digital Sky Survey's Supernova Explorer breaks down complex physics into intuitive sliders. Slide one bar to ramp up the progenitor star's mass, another to adjust its rotation speed, and instantly see how those changes affect the explosion's light curve. Suddenly, abstract concepts like shockwave rebound or radioactive decay heating become visceral. When you disable the titanium-44 decay chain in the simulation, the remnant's prolonged brightness plummets, hammering home how this isotope acts as a cosmic battery. Even VR headsets now teleport users inside the debris field, where 3D spectrographs float like holograms, color-coding elements so you can literally reach out and trace where gold forged in the blast mingles with oxygen-rich gas. But the real revolution is in citizen science. Zooniverse's Supernova Rebuilder project invites anyone to piece together the explosion's history from telescope snapshots, like assembling a cosmic jigsaw puzzle. Your clicks help train AI to spot similar anomalies in other galaxies. Meanwhile, the Gravity Simulator app, developed by a high school coding club, lets you pit this supernova's remnant against hypothetical black holes or neutron stars, watching how gravitational waves ripple space-time during close encounters. The line between gamer and researcher blurs when your gameplay contributes to RZIV research papers. What's astonishing is how these tools reveal the supernova's what-if scenarios. Run a simulation where the star explodes in empty space instead of a gas cloud, and its glow fades on schedule, proof that environment shapes longevity. Reverse engineer the explosion to test if a quark star could explain the energy surplus, and the math spits out magnetic field strengths that match Chandra's observations. These aren't just pretty animations, they're digital laboratories where every user becomes a cosmic detective, testing theories against the ultimate cold case, a star's death that refuses to fade into the night. The universe may be light years away, but its secrets are now hiding in plain sight, waiting for you to click, swipe, and explore. Who knows, the next breakthrough might not come from a telescope's lens, but from your laptop screen where the cosmos dances at your command. There's something profoundly humbling about staring into the aftermath of a star that refuses to fade, a cosmic whisper that tugs at something deeper than scientific curiosity. This supernova isn't just a puzzle for astronomers. It's a mirror reflecting our own fleeting existence against the canvas of deep time. Think about it. That light traveled millennia to reach us, outliving civilizations, outlasting empires, persisting long after the humans who first recorded its appearance turned to dust. And yet here we are, tiny and temporary, stitching together its story with tools our ancestors couldn't have dreamed of. It's a reminder that wonder isn't just the domain of experts, it's encoded in our DNA, the same primal awe that led ancient cultures to weave myths around the stars. What does it mean to witness an event that defies the very laws we've written to explain the universe? There's a quiet rebellion in this supernova's persistence, a cosmic middle finger to the idea that everything must fade on schedule. Maybe that's why it resonates so deeply. In a world where we're bombarded with expiration dates on food, on trends, even on relationships, here's a stellar corpse that says, "Not yet." It's a celestial underdog story, and who doesn't love an underdog? But the real magic lies in how it connects us across time. That same light now hitting our telescopes once illuminated the faces of medieval monks huddled over star charts, of Polynesian navigators steering by its glow, of a child somewhere in the Indus Valley staring up in wordless wonder. We're all part of an unbroken chain of observers, each generation adding its own chapter to the star's story. In an age of division, that's a rare thread of unity, a reminder that the night sky is humanity's oldest shared heritage. And then there's the existential punchline. This supernova's prolonged death throes are happening in what amounts to a cosmic blink. Even its millennia of defiance are just a sneeze in the universe's timescale. It's like watching a mayfly live out its single day and thinking, what resilience, while galaxies spin silently overhead. Yet there's beauty in that disproportion. Our ability to marvel at such fleeting grandeur, to assign meaning to a speck of light in the void, might be the most human thing we do. Perhaps that's the ultimate lesson. Science can measure the titanium in its debris, map its shockwaves, debate its energy sources, but the supernova's true gift is the way it dissolves the boundary between observer and observed. We're not just studying a star, we're in conversation with it, adding our voices to a dialogue that began long before us and will continue long after. And if a ball of plasma can teach us to embrace anomalies, to find comfort in the unresolved, then maybe its light isn't just reaching our eyes, it's illuminating something in us too. When astrophysicist Dr. Elena Vasquez first examined the supernova's erratic light curve, her initial reaction was to question her instruments. The data looked like noise at first, too messy to fit any model, she admits. Her team at the European Southern Observatory spent months ruling out calibration errors before confronting the truth. They were seeing something entirely new. Vasquez now champions the collision cascade theory, arguing the explosion's lopsided debris keeps slamming into pre-existing gas clouds at odd angles. It's like throwing rocks into a pond, then dropping boulders where the ripples intersect. The energy doesn't dissipate, it compounds. Across the Atlantic, MIT's Professor Roger Mehta disagrees. His simulations suggest a hidden magnetar, a neutron star with magnetic fields a quadrillion times Earth's, is pumping energy into the system like an invisible generator. The remnant's polarized emission patterns match what we'd expect from a rapidly spinning, magnetized core, he explains, but there's a catch. No pulsar signals have been detected. Mehta counters that the magnetar could be obscured by debris or spinning at an angle that beams radiation away from Earth. Absence of evidence isn't evidence of absence, he insists. Meanwhile, Dr. Aisha Zhu of the Shanghai Astronomical Observatory proposes a radical third option: dark matter annihilation. Her models show how weakly interacting massive particles WIMP trapped near the remnant could collide, releasing gamma rays that reheat the debris. We're not saying it's definitely dark matter, she cautions, but if you eliminate the impossible, whatever remains, however exotic, must be considered. Skeptics point out this requires densities of dark matter higher than typically observed, but Zhu fires back. Since when has the universe cared about our expectations? The debate turns philosophical with Dr. Kwame Nkosi, a South African theoretical physicist who questions our fundamental frameworks. We're trying to fit this supernova into categories based on a handful of well-behaved examples, he argues. What if normal supernovae are just the simple cases, the hydrogen atoms in our periodic table of stellar deaths? His team is exploring hypernova models where the progenitor star's rapid rotation creates a sustained energy release, like a top wobbling as it spins down. Amidst the disagreements, one consensus emerges. This supernova is rewriting the rules. As Vasquez puts it, the universe isn't obligated to make sense to us. Our job is to keep listening, even when it whispers in riddles. Meta likens it to early quantum mechanics, a confusing puzzle that eventually revealed deeper laws. Zhu sees hope in upcoming neutrino detectors, which could catch particles emitted by a hidden compact object. Nkosi, ever the iconoclast, smiles. Maybe the star didn't get the memo that it was supposed to die quietly. What makes their clash so productive isn't just the diversity of ideas, it's the shared humility. Each expert acknowledges the gaps in their theories, inviting colleagues to poke holes. This collaborative tension, this willingness to be wrong, is how science turns anomalies into breakthroughs. As telescopes grow sharper and simulations more sophisticated, one thing's certain: the final answer, when it comes, will be stranger than any of them imagined. Want to be the first to know when astronomers crack this cosmic case? The story of this supernova isn't locked away in academic journals. It's unfolding in real time, and you've got a front row seat. Start by bookmarking NASA's Astronomy Picture of the Day, where stunning visuals of celestial anomalies often debut with plain English explanations. For deeper dives, follow the RZIV Astrophysics preprint server. It's where groundbreaking research lands before peer review, letting you track discoveries as they happen. Don't let the technical jargon intimidate. Sites like Astrobytes break down complex papers into bite-sized summaries written by grad students who actually make astrophysics fun. If you're craving real-time updates, Twitter remains an unlikely hub for cosmic chatter. Astronomers like Dr. Katie Mack and Phil Plait live tweet telescope alerts and debate theories in threads that feel like a virtual coffee shop for space nerds. Prefer podcasts? Tune into the Supernova Chronicles series from BBC's Sky at Night, where host Dr. Maggie Adarin Pocock interviews the scientists wrestling with this remnant secret. And don't overlook YouTube's own treasure trove channels like PBS Spacetime and Dr. Becky regularly dissect new supernova findings with animations so clear you'll feel like you're floating through the debris field. For a hands-on enthusiast, nothing beats joining the hunt yourself. Platforms like Zooniverse's Supernova Sleuths let you sift through telescope data from your couch. Some volunteers have even co-authored papers after spotting anomalies professionals missed. Local astronomy clubs often organize star parties where you can peer through telescopes at the remnant's host galaxy, watching its flickers with your own eyes. And if coding's your thing, GitHub hosts open-source projects analyzing the supernova's light curves, perfect for aspiring data scientists to cut their teeth on real cosmic puzzles. The most thrilling part: this isn't just spectator sport. Citizen scientist Thomas Jacobs famously discovered a supernova's precursor, flare, using free software, a proof that breakthroughs aren't reserved for those with PhDs. Whether you're scrolling through curated space news or contributing observations, remember, every major discovery began with someone asking, "What's that weird thing over there?" The universe is writing its next chapter, and your curiosity might just hold the pen. As we reach the end of our cosmic detective story, it's worth pausing to reflect on what this stubborn supernova truly represents. It's not just an astronomical oddity, it's a glowing testament to the universe's boundless creativity, a reminder that even our most carefully crafted scientific models are just rough sketches of reality's masterpiece. Think about it, every textbook rule this explosion shattered was once considered ironclad. Every assumption it overturned was born from decades of observation. Yet here we are, humbled and exhilarated by a star that refused to follow the script. This isn't just about astrophysics, it's about the very nature of discovery. Centuries ago, when early astronomers first recorded guest stars in their scrolls and charts, they had no telescopes, no spectrographs, just naked eyes and boundless curiosity. Today, we're standing on their shoulders, wielding technology they couldn't have dreamed of, yet facing the same fundamental wonder. That thread, from ancient stargazers to modern scientists peering through space telescopes, connects us all in a shared pursuit of understanding. The supernova's lingering light becomes a metaphor for human perseverance, proof that some questions are worth chasing across generations. So what's next? The universe hasn't run out of surprises. For every mystery we solve, a dozen more emerge, each more tantalizing than the last. Maybe the next great anomaly is already flaring in some distant galaxy, its light racing toward us even as we speak. Or perhaps it's hiding in plain sight, buried in old data, waiting for a fresh perspective to uncover it. That's the thrill of science, it's never finished. There's always another layer to peel back, another assumption to test, another cosmic rebel waiting to rewrite the rules. Before you go, take this with you. Every time you look up at the night sky, you're participating in the oldest human tradition. Whether you're spotting constellations with your kids, adjusting a telescope in your backyard, or simply pausing to marvel at a particularly bright star, you're part of the story. The universe doesn't discriminate, it reveals its secrets to anyone willing to ask. What if? So keep wondering, keep questioning, and above all, keep looking up. The cosmos has a way of rewarding those who pay attention, and who knows, the next great discovery might just have your name on it. Now it's your turn. What fascinates you most about this cosmic rebel? Have you ever spotted something in the night sky that made you pause? Drop your thoughts below. The conversation is just as important as the science. After all, curiosity is contagious, and every great discovery begins with someone daring to say,